Welcome back to Mechanical Design 1 course. Today's topic is about stress, strain, and deflection. Outline of this presentation is as follows. Stress components and notation, a stress tensor and notation, strain, principal stresses, principal normal and shear stresses, plane stress transformation equations, extreme value of shear, Moore's circles, constructing Moore's circle. Stress, force per unit area is stress. So your unit of the stress is PSI or megapascal. Every element in a part is subject to a stress and can be modeled as a cube. So in three-dimensional cases, we could take one infinitesimal element in the shape of a cube from our part in any point of the part. So this cube represents one point in our part. Okay, for each point inside our part, we could have one of these cubes. Normal stresses act perpendicular to the faces of the cube and tend to either pull it out or push it in. So here, sigma xx, sigma yy, and sigma zz are all normal stresses, and they either compressive or tensile. They either pull it out or push it in. Shear stresses act parallel to the faces of the cubes in pairs on opposite faces, which tends to distort the cubes into rhomboidal shape. So here we see our shear stresses. We have tau yx, and on this face we have tau xy. That's why we say they are in pair on opposite faces. Tau xy is equal to tau yx. And you see that they tend to distort this cube. They want to change the shape of the cube from a perfect cube to a rhomboidal shape. But normal stresses just they either expand or contract the cube. So the shape of the cube will stay as a cube. It doesn't change the shape, but they tend to change the volume. So we are talking about normal stresses. Yes, so normal stresses keep the shape but change volume, change volume of the cube. Shear stresses, they tend to distort the cube. These normal and shear components of stress acting on an infinitesimal element make up the terms of a tensor. So this one is infinitesimal element, it's very small. This cube represents one point of our part. And all of these stresses on this cube shape or make up our stress tensor. Here we have positive stress components, and here we have negative stress components. So for the normal stresses, it's very clear. They are tensile stresses and they are outward. And for shear stresses, you see they basically face or point to the same edge. So tau xy and tau yx are pointing to one edge. But in negative stress, for normal stresses, they are compressive or they are inward, and for shear stresses, they are pointing to two different edges. See tau x y and tau y x. Okay, so here we have our surface normals. What are I, J, and K based on our right hand Cartesian coordinate system? Okay, this one is a right hand Cartesian coordinate system. And based on these I, J, K, or normals to the surfaces, they have positive stress components and negative stress components. Here we have two-dimensional stress element, okay, that shows only one face of this cube, and is good for analyzing two-dimensional problems to avoid complexity and redundant information. Here you could see we have sigma xx, which is positive, sigma yy is positive, tau xy and tau ix, both here positive. And as we said, tau xy and tau ix are equal. Why? Because this cube is in static status. It's not moving, okay, or in quasi-static status. So if we write sigma f and sigma y equal to 0, or write the equilibrium equation, static equilibrium equation, so we see that tau xy here should be equal to tau ix. We'll discuss this more in coming slides. Okay, so the 3D stress tensor can be expressed as the matrix. Okay, now we want to organize our stresses and put normal stresses in the diagonal arrays of our matrix. So here we have sigma xx, yy, and zz are normal stresses. Tau xy, tau xz are shear stresses. You see that it starts with x. Okay, so we have it in the first row. Then we have tau yx and tau yz and tau zx and tau zz. You see how we are organizing this tensor matrix of stress. And the stress tensor for 2D is 2 by 2. We have sigma xx, tau xy, tau yx, and sigma yy. Sigma xx and sigma yy are normal stresses. Tau xy and tau ix are shear stresses. Dual subscript notation can be reduced to sigma xx, sigma yy, and sigma zz could be reduced to sigma x, sigma y, and sigma z. It's just for the matter of simplicity, yes? For the sake of simplicity. Due to symmetry, tau xy should be equal to tau ix, tau iz is equal to tau zy, and tau zx is equal to tau xz. So our matrix is symmetric. A stress and a strain are linearly related by Hooke's law in the elastic region of most engineering materials. So before we had a formula for tensile only, tensile stress test only, that sigma x was equal to E epsilon x. But that Hooke's law could be expanded for 3D cases and for a stress and a strain tensor. A strain can be expressed for 3D case as a matrix epsilon xx, epsilon yy, and epsilon zz are normal strains, and epsilon xy, epsilon xz, epsilon yx, epsilon yz, epsilon zx, and epsilon zy are uh, basically shear strains. And this matrix is symmetric. For 2D case, again, we could reduce this matrix to 2 by 2 matrix. And we will see we only have epsilon xx, epsilon y in diagonal arrays, and epsilon xy and epsilon yx in off-diagonal positions, where epsilon represents either a normal or shear strain, the two being differentiated by their subscripts only. Okay, so we have normal and shear strain. The same symmetric relation shown for shear stress components in the above equation also apply to the strain elements. So epsilon xy is equal to epsilon yx. Principal stresses. The axis systems taken in above figures are arbitrary and are usually chosen for convenience in computing the applied stresses. Okay, what do we mean by that? So the cube we selected in one particular point. So that cube was representative of a point in our part. The rotation of that cube is based on the applied stresses. Is based on the stresses applied from the environment or externally to that point. So it's easier to do analysis and write the stress and strain tensors. Okay, but we could change the rotation of that cube. Yes, so the point at the center of the cube is constant, but the cube could rotate. For any particular combination of applied stresses, there will be a continuous distribution of a stress field around any point analyzed. Okay, so for any applied stresses, we could have a distribution of stresses or specific stress tensor for that point. The normal and shear stresses at the point will vary with direction in any coordinate system chosen. So if we change the direction of the coordinate system but keep the center of that coordinate system in or targeted point, then the value of stresses on the cube changes. There are always planes on which the shear stress components are zero, and the normal stresses acting on these planes are called the principal normal stresses. The planes on which these principal stresses act are also called principal stresses. So if we rotate the cube and in one particular direction, we find out that shear stresses, components of shear stresses are zero, then we are in principal coordinate system. And stresses applied or normal stresses applied to the faces of that cube are principal normal stresses. There will be another set of perpendicular axes along which the shear stress will be maximal. Okay, but these are not principal normal stresses coordinate system. The principal shear stresses act on a set of planes at 45 degrees to the planes of the principal normal stresses. We'll discuss further the detail of these when it comes to more circle and calculation of principal normal stresses and principal shear stresses. So don't worry if you didn't get the detail of this slide. It was just a guide for coming slides. Principal normal and shear stresses. Here we could see that we have one element, one cube element in one specific point of our part. And the direction we chose, or the coordinate system we chose for this cube, is based on the applied stresses, is based on the forces and the stresses applied to the part, and it's easier for us to analyze our stresses based on this coordinate system. That's why we chose this specific coordinate system. Again, this cube represents one point of the part. Now, on that point of the part, we could just choose different coordinate systems. We could choose this specific coordinate system and rotate our cube to represent that coordinate system or any other coordinate systems. By the definition, if we keep rotating this coordinate system, we could reach to a specific coordinate system where we don't have any shear forces on the sides of the cubes. So here, you see that the shear forces are 0. We only have normal forces, sigma 1 and sigma 3. These normal forces now are principal normal stresses. And we need to find what is this phi angle, how much we should rotate this coordinate system from the applied coordinate system to reach to this principal normal stresses or coordinate system. We'll do the calculation later. And if we rotate the cube again, we could reach to principal shear stresses, where the principal shear stresses are maximum. Okay, so this one is principal shear stress coordinate system. Okay, so these shear stresses are maximum. So either 0 for principal normal stresses or maximum for principal shear stresses. And we need to find what is this theta. Theta, okay. Okay, so plane stress transformation equations. Now we want to see what is relation between a stress tensor in one coordinate system and the other. Okay, so here on this one, we have applied the stresses, sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. Okay, and here we have the 2D case and apply the stresses. Okay, now imagine that we choose a different coordinate system, a random different coordinate system, not really a specific one. So we just rotate our coordinate system from xy to x prime, y prime. Okay, so now I have x prime, y prime coordinate system, and we want to calculate the stresses on this new coordinate system. How much we rotate the original coordinate system, theta. Okay, so we need to basically cut the cube and find normal and shear stresses on the surface of the new coordinate system of x prime and y prime. So here, now we have this element And on this element, we have sigma x acting on this side, sigma y, tau xy on these sides, and on this new side, sigma x prime and tau x prime y prime. Okay, so these are the stresses, normal stresses and shear stresses by definition in x prime y prime coordinate system. Why by definition? Because by definition normal stress should be perpendicular to the surface and shear stress should be parallel to the surface. Okay, so what are basically the area of these sides? So imagine this new side, this rectangular, the area is A. So this side on the left, the area of this side on the left will be A cosine of theta, and this area will be A sine of theta. And now we could find the forces acting on this element. If we just multiply stresses to the applied area. Okay, so summation of forces in y prime and x prime direction gives. So if we calculate sigma x, sigma f x prime and sigma f y prime, which should be equal to 0. Why? Because the element is in equilibrium, is in a static state. Then we could find a relation between sigma x prime and sigma x and tau xy. So here, back to the previous slide and check if this equation is correct and holds. And if we consider all of these elements on the x prime axis and do the same for the y prime axis. After solving the normal and shear stress for new planes, we could find sigma x prime and tau x prime y prime as a function of the stresses in the x and y coordinate system. So now we have sigma x prime as a function of sigma x, sigma y, tau xy, and theta. So now you could see how we could find the principal normal stresses where the tau x prime, y prime is 0. We need to find what is the value of theta. And now we could also find the maximum tau x prime, y prime by getting a partial derivative of this equation based on theta and then find theta. Recall from trigonometry, sine of 2 theta is equal to sine of theta cosine of theta, and cosine of 2 theta is equal to cosine square of theta minus sine square of theta. So if we use these equations in the previous equations, then we could simplify the sigma x prime and tau x prime y prime functions, and we could yield these equations. I'm going to leave this to you to find out how they managed to simplify those equations by these relations. Okay, so these equations are basically fundamental of also Moore circuit, and you see that we could easily calculate these equations based on Moore circuit, analyze it, and Moore circuit is nothing basically more than these two equations. Okay. To find principal plane, set the tau to 0 and solve for theta. So tau should be 0 based on definition, and then we could find theta p for principal, normal, stress or principal coordinate system, and the tangent of 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y. Again, try to find this equation by yourself. It's a good practice. Values of normal principal stresses then will be sigma 1 and sigma 2. So from now on, we show principal normal stresses by these subscripts, sigma 1 and sigma 2. And sigma 1 is always more than sigma 2 by definition. Okay. What you need to do, you need to just plug this equation in a sigma x prime function to find principal normal stresses. And we just call those principal normal stresses sigma 1 and sigma 2. Okay. To find maximum shear stress values, could find a new angle theta 2s. The tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 tau xy. At the maximum shear stress, normal stress will be sigma x is equal to sigma x plus sigma y divided by 2. Okay, these are not, again, rocket science. All of these equations come from sigma x prime and tau x prime y prime functions, and you could easily find them. Okay, so it's a very good practice to first familiarize yourself with those two functions and understand the meaning of principal stresses and principal normal and shear stresses. And then we could find extreme values of shear or principal shear stresses. Again, we call them tau 1 and tau 2. So these tau 1 and tau 2 are basically tau x prime y prime while they are at extreme value. And now these are principal shear stresses, and you see the equation. Okay, try to drive all of these equations yourself again, based on sigma x prime, tau x prime, y prime. It's a very good practice. Okay, Morse circle. Morse circle have long provided the mean to find the principal stresses for the plane stress case. Okay, so it's basically alternative solution for those sigma x prime, tau x prime, y prime functions. Okay, it's nothing, basically doesn't give us anything more, just a very illustrative tool that could make our life easier. Is very intuitive to understand, and it's very easy to do the calculation and recall the formula. Many textbooks on machine design present the Morse circle method as a primary solution technique for determining principal stresses. Anyway, they are the same as those functions. So Morse circle will give us the same equations and same numbers. It can serve as a quick check on a numerical solution. It also serves the useful purpose of providing a visual presentation of the stress state at a point. Okay, so this visual presentation is very important. And once you learn Morse circuit, you will forget those equations that we had for the sigma x prime and tau x prime y prime. Okay, so what is the Moore circuit? We'll go slide by slide and see how we'll construct Moore circuit. Okay, but here a brief introduction on this slide. On the x-axis, we have normal stress as sigma, and on vertical coordinate axis, we have tau or shear stress. Okay, so always we have one line which is intersecting the circuit and gives us applied stresses. Okay, so in this case, we have sigma x, tau xy, and you have sigma y, tau xy. So these are the normal and shear stresses on one side of the cube, and these are normal and shear stresses on the other side. You could rotate the AB line to find stresses on other coordinate systems. You see that normal principal normal stresses sigma 1 and sigma 2 on the x-axis. Okay, so plus here you see the value of tau xy, and the maximum value of tau xy happens at the point F, which is principal shear stress. Okay, so we'll go slide by slide, see how we could construct this more circuit and how you could work with that. What I suggest you to do, to take a paper and pencil right now and try to construct a more circuit by yourself. Plus, once we reach to the example, try to draw your circle on paper and construct it by yourself. Constructing Moore circle. Perform the stress analysis to determine the magnitudes and directions of the normal and shear stresses acting at the point of interest. So first, we need to find stresses. We need to find applied stresses, either normal or shear stress. This is the first point, where we should calculate them at the point of interest. Normal stresses on any two mutually perpendicular planes are drawn with tensile stresses positive projecting outward from the element, and compressive stresses are negative directed inward on the face. Constructing Moore circle. Shear stresses are considered to be positive if they tend to rotate the element in clockwise direction and negative otherwise. Again, we are in constructing Moore circles, so all the definitions for positive and negative value of normal stresses and shear stresses are solely for Moore circle, not for a stress tensor. So for the normal stresses in the Moore circle and the stress tensor, by definition, they are the same. When they are outward or tensile, the value of them are positive. So sigma x here in this element is positive. And sigma y is negative because it is inward. Okay, and it's compressive, both for the Moore circle and stress tensor. But for the tau xy here, by definition of the stress tensor, tau xy and tau yx both are positive. But in Moore circle, tau xy tend to rotate the element clockwise. So tau xy is positive. So what What do we mean by clockwise? This direction, yes. This direction is clockwise. So tau xy tend to rotate the element clockwise. And tau yx tends to rotate the element counterclockwise. So tau yx is negative. Okay, this definition is solely for Mohr circle, but in reality, both of them are positive. Why? Because they are pointing to the same edge, to this edge. Okay, to this edge here. Next step is to set up a rectangular coordinate system in which the positive horizontal axis represents positive normal stresses and the positive vertical axis represents positive shear stresses. Thus, the plane created will be referred to as the sigma tau plane. Okay, now we need to construct this sigma tau plane. How we could do that? We have two sides. Yes, we have x side on the element and y side. On the x side, we had tau x and tau xy. Sorry, sigma x and tau xy. Both of them are positive. So see, we are in positive quarter of the coordinate system. And on the other side, we had sigma y, which was negative, compressive. And we had tau yx, which was also negative. So you see, we are in the third quarter of the coordinate system. Okay, so the next step is basically to locate these 2 points, A and B point, sigma x tau xy and sigma y tau yx in sigma tau coordinate system. Once you have these 2 points, okay, so A point, okay, and let's say B point, okay, we have 2 points now, okay. Once we have these 2 points, we could just draw a line between them, find the intersection of that line with the sigma coordinate system, and find O. And this O is basically the center of Mohr circle. And R or OA or OB is radius of the Mohr circle. Now we could easily construct our circle and find the radius of the circle, find the center of the circle. So what is the center location? It's the average of sigma x plus sigma y divided by 2 will be the location of O. How much is R or radius? It's a square root of a square plus b square. What is A? Is sigma x minus average, and B is equal to tau xy value. You see, we could easily find the center of the circuit and the radius of the circuit. Now we almost constructed our circuit. Okay, now we have our circuit and see how we could use this circuit. Plot points on sigma tau plane corresponding to the stresses acting on the faces of a stress element. which we already did. We call that A and B point. If the element is drawn in the xy plane, the 2 points to be plotted are sigma x tau xy, A point, and sigma y tau yx, B point. These are 2 points on Mohr circle. Draw the line connecting the 2 points. This is the line, AB line. The resulting line crosses the sigma axis at the center of Mohr circle at the average of the two applied normal stresses, where sigma average is equal to sigma x plus sigma y divided by 2. Okay, so O point is sigma x plus sigma y divided by 2. The center of Mohr circle is called O. Now it is important to note that the line from the center of Mohr circle at O and draw the first plotted point sigma x tau xy represent the x-axis from the original stress element. Draw and label an extension of this line at this point. Angles of rotation for the principal stress element and the maximum shear stress element will be measured from this axis. So you see now, if we find these two angles, okay, if you find these two angles, theta P and theta S, then we could see how much we need to rotate this element to have sigma 1 and sigma 2 stresses, or principal normal stresses. So if that AB line sits on the x-coordinate axis, then the stresses on the element will be equal to principal normal stresses, and shear stresses will be 0. Okay, a right triangle has been formed. So this is a right triangle here, having the sides A, B, and R. A, B, and R, where R is square root of A square plus B square, and A is sigma x minus sigma average, and B is equal to tau xy. The angle alpha within the triangle between lines A and R. So this is the alpha. Okay. Between the A and R. The alpha is tangent square, tangent inverse of B divided by A, or alpha is sine inverse of B divided by R. Okay. Again, have your paper and pen and try to construct a Mohr circle. Find these equations by yourself one by one and see where are they coming from. If you could calculate and find these equations, if you could find the radius of the Mohr circle, the center of that, the alpha angle, okay? Draw the complete circuit with the center at O and radius of R as shown. Okay, now this is Mohr circle. It is important to realize that the angles on Mohr circle are actually double the true angles. Okay, so here we have our element. If we need to find a principal coordinate system, we need to rotate this element by basically phi sigma, not 2 phi sigma. So if we calculate this angle and find that, for example, this one is 60 degrees, in reality, we need to rotate this angle only 30 degrees. Where should we rotate that? If we rotate it clockwise, then the x-axis will sit on the principal coordinate system, and sigma x will be equal to sigma 1, and sigma y will be equal to sigma 2. So you see that if we rotate this element clockwise, sigma x, or this point, will come and will sit on sigma 1. So sigma x will be equal to sigma 1, and sigma y will be equal to sigma 2. So you see that now, by rotating the line of sigma x, sigma y, you could find how much we need to rotate this element, and then how much will be the value of stresses on the new coordinate system. Okay, so again, the more circuit is based on the sigma x prime, tau x prime, y prime function. Okay, it doesn't give us anything more than that, but it's just a very visual method to calculate formulas and find principal stresses and coordinate systems. Okay, now we could find sigma 1, the maximum principal stress at the point where the circuit crosses the sigma x at the right. Note that sigma 1 is equal to sigma average plus r. So sigma average was basically the value of stress at point O, plus r was the radius of the circle. So sigma 1 could be easily calculated based on the circle. And we could find sigma 2, the minimum principal stress at the left end of the horizontal diameter here. Note that sigma 2 is sigma average minus r. Okay, so sigma average plus r and minus r were the equation we already had for sigma 1 and sigma 2. Refer to the previous slides and see what was a sigma 1 and sigma 2 equation. You see that they are exactly the same. Now we could find sigma average, a maximum shear stress point, this point, or sigma average tau max at the top end of the vertical diameter of the circle. By observation, tau max is equal to r, or the radius of the circle. The radius of the circle, r. Note also that the coordinates for the point at the top of the circle are sigma average tau max. Okay, so now also we could find this phi tau, and if we rotate our element, or this one was apply the stress coordinate system based on that apply the stress coordinate system. So if you rotate that by phi tau, we could then have maximum shear stresses on the side of this element. So here, for example, see that they rotated the applied coordinate systems by phi sigma, and now on our element, on this new element, we have maximum normal stresses, sigma 1 and sigma 2. And we don't have shear stresses. Why? Because shear stresses at these 2 points are 0. Again, these are just different representation of stresses on one particular point of our part. Okay. Could find the angle called 2 phi A. always measure from the x-axis to the sigma axis. 2 phi A is equal to alpha, and the rotation is clockwise. In other problems, the angle must be found from the geometry of the circle. Now compute phi sigma is equal to 2 phi sigma divided by 2. So what is important for us is phi sigma. All the angles in the Mohr circle is twice the real angles in element rotation. Here you see that we found also theta, and we rotated the element based on this theta. See, we have maximum shear stresses, we call them principal shear stresses, and normal stresses, sigma x and sigma y are exactly equal, and we call it sigma y because at the principal shear stress coordinate system, while we are at this vertical line, you see that normal stresses of these 2 points, this one A and B points, are equal to the value of the O location or sigma average. Could find the angle called 2 theta, always measure from the x-axis to the palm axis. And note the direction either clockwise or counterclockwise. So we could either rotate it from this side or to this side, and it doesn't matter. If we rotate it, let's say counterclockwise, we need to rotate our element counterclockwise. In the current problem, we can observe that 2 theta is equal to 90 minus alpha, and the rotation is counterclockwise. Okay, so you see that now we have very nice phenomena here, that the difference between a principal normal coordinate system and principal shear coordinate system is 90 degrees in Mohr circle, and in reality is 45 degrees. Draw the maximum shear stress element as shown. A new element in relation to the x-axis at an angle of theta. The new element must be rotated in the same direction. You see that this is the new element. On the maximum shear stress element, the average normal stress acts on all 4 faces. So the average one, the value of the center of Mohr circle O, is acting on all faces. The final step in the process of preparing Mohr circle is to summarize the primary results, typically sigma 1, sigma 2, tau max, sigma average, phi sigma, and phi tau. This is the final step. Okay, now we will have one example on Mohr circle. Stress element has sigma x equal to 80 megapascal and sigma y is equal to 0, and tau xy is equal to 50 megapascal clockwise. These are applied stresses, and we said that the first step normally is to find applied stresses. We'll do that in the coming sections and chapters, and you see in real analysis and problems how we could find applied stresses, but for the purpose of teaching Mohr circle, these values are given. Goals are using Mohr circle, find the principal stresses and directions. Show them on a stress element correctly with respect to the xy coordinates. Draw another stress element to show tau1 and tau2. Find corresponding normal stresses and label the drawing completely. Okay, so before proceeding to the solution, I strongly suggest you to have your paper and pen ready and try to review the construction of the Mohr circuit by yourself and see if you could construct the Mohr circuit yourself, find principal stresses of sigma 1 and sigma 2, maximum shear stress tau max, if you could find phi sigma and phi tau. Okay, so first, before proceeding to the solution, try to do the calculation yourself and then check your solution with the provided solution. Okay, so let's start the solution here. What we need to do first, we need to draw our stress element. This is our stress element with the x and y coordinate system, Cartesian coordinate system. Based on the problem, we have sigma x equal to 80 megapascal and sigma y is equal to 0. And tau xy is clockwise, okay, so it's clockwise, and is equal to 50 megapascal. But in stress tensor, this value is negative, is not positive, yes? So for the purpose of the Mohr circle, it's positive, but for the tensor, for the stress tensor is negative. Okay, so why is that negative? Yes, so first is tau xy. So x, the first one, x, shows that we are in the x plane. So we have in a plane perpendicular to the x. And y, the second one, shows that the direction of the stress is along with the y-axis. Y is negative, or its opposite direction of the unit y or j vector, so is negative. Okay, so we need to first draw our stress element with sigma x, sigma y, tau xy, and tau yx. Okay, and after that, once we have our stress element ready, we could move on to the Mohr circle. So here you could see that we have in the Mohr circle, in the x-axis, we have normal stress or sigma, and in the y-axis we have shear stress or tau. Okay, so now the next step is to draw our Mohr circle or construct our Mohr circle. How could we do that? We need to first find point A and B. Okay, so point A is sigma x tau xy, and tau xy is positive. Why? Because the tau xy here tends to rotate our element clockwise. Okay, so it's positive. So we have sigma x is equal to 80 and tau xy is equal to 50. And point B is sigma y tau yx, and sigma y is 0. And tau yx is negative 50 because the tau yx tends to rotate our element counterclockwise. So you see that always the point A and B, um, they have opposite sign value of the second coordinate or the y coordinate. So the tau xy here is positive, tau yx is negative. If tau xy is negative, then tau yx is positive. But again, in the stress tensor, if you remember, tau xy and tau yx both are equal. both of them are either positive or negative because the stress tensor is symmetric. So when we are plotting the Mohr circuit, we have different convention for the tau or shear stress, and don't mix that with the rules of a stress tensor. Okay, now we have point A and B in our coordinate system. What we need to do, we just need to draw a line between the point A and B, okay, and then draw a circle that passes both point A and B. Plus, we could have point O, which is the sigma average, or sigma x plus sigma y divided by 2. Please refer to previous slides and review the formula. Okay, so now we have our full circle here. The circle now is ready. What we need to do in next steps to find principal normal stresses and principal shear stresses, plus find the element for the principal normal and principal shear stresses. Okay, so in the next step, we will find principal normal stresses, okay, sigma 1. And sigma 1 is equal to sigma average plus r, or radius of the circle. How we could find the radius of the circle? Okay, so the radius of the circle is equal to the square root of sigma x squared plus tau xy squared. Okay, look at this right triangle here. Based on this right triangle, we could find the radius r. We also had the sigma average, so sigma 1, or the first principal normal stress, is equal to sigma average plus r. Moreover, we could find the sigma 2, or the second principal normal stress. What is the value of sigma 2? Is O minus r. Okay, O minus r. Okay, this one is the radius of our circle. Okay, now we have sigma 1 and sigma 2. Now we need to find a stress element which has both sigma 1 and sigma 2 on that. What we need to do, we need to rotate our element. How much we should rotate our element? We should rotate it with the value of phi sigma. So as we said, all the angles in the Mohr circle is double of real angles. So we need to calculate these two phi sigma from the Mohr circle. Okay, how could we do that? We have this right triangle here, and the tangent of these two phi sigma is equal to tau xy divided by this side of our triangle. Okay, so this value is equal to sigma x minus sigma average. Okay, so once we calculate that phi sigma, then we need to rotate our stress element by the value of phi sigma. You see that we rotated that clockwise. Why clockwise? Because the line A should sit on sigma 1 and B should sit on sigma 2. So basically we are rotating this line AB to sit exactly on the horizontal axis or sigma axis. Okay, so point A sits on the point sigma 1, and see that sigma x becomes equal to sigma 1 now in the new coordinate system of x prime, y prime. Okay, we have a new coordinate system now. Okay, this is a new coordinate system, x prime, y prime, and the sigma x prime will be equal to sigma 1. And sigma y prime will be equal to sigma 2. Why? Again, because look, the point B now is sitting on point sigma 2. So sigma y now is equal to sigma 2, and sigma 2 is basically, or sigma y prime in the new coordinate system. Okay, so how much is the value of shear stress now in this new element? For tau x prime y prime is equal to 0. Because in the point sigma 1 and sigma 2, you see we don't have any value for the shear stress, yes? Because we are exactly on the sigma axis or the horizontal axis. So tau x prime y prime is 0, and tau y prime x prime also is 0. So both of them are 0, okay? So now also you see that based on the definition of principal normal stresses, it happens when the shear stress is 0, okay? So now we have the principal normal stress element, and plus we calculated, or principal normal stress is sigma 1 and sigma 2. Okay, now we need to calculate principal shear stress and principal shear stress element. What we need to do, we need to find this phi tau, and we need to rotate our element counterclockwise by phi tau. How could we calculate phi tau? We have this angle here, 2 phi tau, and we have this right triangle here, and by getting tangent of these 2 phi tau, we could find it. So based on the geometry here, we could find phi tau. Okay, so we need to rotate our original element by phi tau counterclockwise, and then on this new element, on the x prime y prime coordinate system, x prime y prime coordinate system, we will have sigma x prime, which is now is equal to the sigma average. Why? Because look, this line AB now is sitting on this vertical axis here. So sigma x prime is equal to sigma average, and tau x prime y prime is equal to tau max. And tau max is or principal shear stress, or tau 1. Yes, sometimes they represented by tau 1. Also, on the other side, you see that when the point B comes to this point here, what is the value of sigma x prime? Sigma x prime is equal to sigma average. And what is the value of the tau? Is equal also to tau max. Okay. Now we have our principal shear stress element, and we have principal shear stress values. So you could note that on principal shear stress, the shear stress is maximum, but the normal stress is not 0. But the normal stress on both x prime and y prime axis are equal to sigma average. I'm gonna leave all the calculations, numerical calculations by yourself to find sigma 1, sigma 2, tau max, or phi sigma and phi tau. So do it by yourself on a piece of paper. It's a very good practice, and you will learn all basically steps.